Hi, now we're back again. So let's go on to problem 44, and it's about three vectors, and we can enter the first component, or the first vector's components using this, and then we can view them as a column matrix using that. So that's the first vector. And now let's take the second one, and we can visualize that as a column vector, or column matrix. And here's the third one, and we can view that using that. So there are two questions. Are the vectors linearly independent? And if not, are the vectors coplanar? I mean, if they're linear independent, then they're not coplanar. Let's start by converting that into a problem in linear algebra. So we're going to construct the matrix. Well, before we do that, notice that these vectors are the same as those in problem 38, which we did last week. Anyway, the vectors are linearly independent if the matrix whose columns are the three vectors is non-singular. So let's construct that matrix. So we take the three vectors and put those into a matrix, and then take its transpose, and which we can view in matrix form using this. And you can see that the first row is 1, 2, 3. Sorry, the first column is 1, 2, 3. The second is 1, 1, minus 1, and so on. So that's correct. Well, the vectors will be linearly independent if this matrix is non-singular. So let's carry out the row reduction. So we want to subtract twice the first row here from the second row, and that will get us a 0 here, and 3 times the first row from the third row. So we do that using this, and we can visualize that using this, and we can see that we have indeed got zeros in the first column. And now we do the same thing on the second row. We take 4 times the second row from the third row and leave the first 2 rows unaltered, and we can see that what we've done here. And we can see that the third row is the 0 vector, and therefore the determinant of this matrix will be 0. So the vectors are linearly dependent, and thus either coplanar or collinear. So that's the next part of the question: are they coplanar? Well, the vectors will be coplanar if we can find unique values of the coefficients a and b, which we can set up using that. Such that the third, for example, is a linear combination of the first 2. So we set up this set of equations. So these 3 equations have to be 0. And we can extract the coefficient matrix using that. And so in other words, we take the coefficient of the jth parameter in the ith equation, and then we can calculate the right-hand side vector by multiplying the coefficient matrix times the parameters and subtract off the equations. And we can construct the augmented matrix for this using this and view it in matrix form like so. And we can see that this is the same as the matrix in the first part, but anyway, we might as well repeat the row reduction. So we subtract twice the first row from the second, and 3 times the first row from the third, and we can view that like so, and then we repeat it to get the, and this will be the same matrix as we got before, but now we want to do something slightly different. Well, we can interpret this as an equation which says that 0 equals 0, so that's good. And now we can look at the second row here and regenerate the equations. So we take the second row of the matrix and multiply it by the vector which consists of the parameters and -1 added to them, and that will give me that, which tells me that b is equal to 2, which we can generate like that. And then we take the equation presented by the first row. We can generate that equation using this, and we can simplify that by using the value of b, and that will give me an equation for a, which has the obvious solution a equals 1. And so we have found unique values for a and b such that the third vector is a linear combination of the other two. We can check that using that by multiplying the coefficient or regenerating the equations and then inserting the solutions, and we can see that that is indeed the third column.